It's the first time in my life I have a talk for so broad audience with really different backgrounds. So I tried to do my best, but I don't know how it, whether you will be happy or bored. But anyway, so I will talk about dynamics of topological. Dynamics of no, okay, it doesn't matter. Now it will. Okay, it works. So I will talk about dynamics of topological solitons because it's like a big part of my professional interest, and it can be more interesting for you because you are also interested in topological solitons, although in completely different physical systems or mathematical setup. So first of all, I will tell you about my physical motivation, and it will be about topological solitons in nuclear physics or high energy physics, in theories which are much more related to fundamental interactions. And then I will concentrate on the role of vibrational modes of these solitons. These are modes, like the name it is, which allow solitons to vibrate. Okay, it's a kind of internal degrees of freedom hosted by solitons. And then I will tell you how these internal modes how they are important for the dynamics of topological solitons. And this is completely general. It doesn't necessarily apply only for solitons in high energy physics or nuclear physics. It applies for any topological solitons, okay, provided their dynamics is not in strongly damped regime. Okay, so it's a kind of second order dynamics or conservative dynamics or dynamics with inertia, okay, like usual Newton equations. And then I go a little bit deeper into ways how topological solitons interact, that they can feel a static force between themselves. There are these internal modes, and there is also radiation, which takes energy from solitons to infinities, for example. And then I will talk about, I wanted to talk about 4 features, but I think I will talk about 2 features, which are resonant energy transfer mechanism, which couples internal degrees of freedom to kinetic degrees of freedom, and something which we call spectral wall phenomenon, which is also related to internal modes. It happens when internal modes disappear, cease to exist, okay? Okay, so topological solitons in nuclear physics or high energy physics. The fundamental theory of strong forces, right, it's QCD. And we know it very well, but we can do fantastic computations in a perturbative regime, right? Where quarks are really fundamental degrees of freedom. We can expand in Feynman diagrams and compute many things like cross sections and really understand the theory. But the world around us is not in this perturbative high energy regime, but in the low energy regime where we don't see quarks any longer. We have proton, neutron, atomic nuclei, and then we have nuclear matter in neutron stars, which we know that they exist, okay? So how to understand these objects? We do something like effective field theory, okay, where quarks are not any longer degrees of freedom, but the quasi-fundamental degrees of freedom are the lightest Goldstone bosons related to the fundamental theory, to the QCD, okay? And these are mesons, the lightest excitations in the theory, pions, Okay, they are the lightest particles. So the idea is to build a model where pions are the fundamental particles, and we have only 3 pions, pi 0, pi plus, pi minus. Okay, so you have 3 degrees of freedom, and then you would hope that all other objects, baryons, atomic nuclei, and so on, would emerge from this theory. You wouldn't like to add them as a new degrees of freedom. Okay, it's less attractive to build a theory with 100 particles. It's better to have only 3 fundamental particles and the rest like some emergent phenomena. And this is exactly the theory proposed by SKCM many years ago, based on pionic degrees of freedom. Okay, and then all other objects are solitons, topological solitons. Okay, and this theory was just proposed, okay, with this motivation, but we got strong support from large NC color limit. Okay, in this limit, where the number of colors goes to infinity, and colors is a like gauge group of the QCD. If this number of colors goes to infinity, then we know precisely that the limit of the theory is just a purely mesonic theory, okay? But we do not know the action. We know only the degrees of freedom. So you can hope that our universe, or our world, where we have only 3 colors, it's still close to infinitely many colors limit, okay? Okay, so let's assume that this is a plausible assumption, okay? And look into the simplest case, we have these 3 pions, okay? And they are somehow disguised into SU2 matrix field, okay? So we have a field of SU2, it belongs to SU2 group, or equivalently, you have 4 real fields which modulus equals 1. So they live on a 3-dimensional sphere, okay? The target space is 3-dimensional sphere. So now you see how topology enters in this theory. If you take this field, okay, and this field at static configurations, it's a map from 3-dimensional space where we live, okay, to SU2. SU2, as you see, it's like 3-dimensional sphere. But if you assume that this field at any point at infinity has the same value, okay, it's the same matrix. So basically you add a point at infinity. So such a manifold, which is compactified 3-dimensional space, is just S3. Okay, and now you have mapped from a 3-dimensional sphere into 3-dimensional sphere, and this is all these maps are classified by a 3rd group homotopy, okay, with topological charge, and we know precisely that this topological charge it's the baryon charge, right? It's rigorously proven. It has been rigorously proven that the topological charge of this field is really the baryon charge of the QCD. Okay? Good. So, okay, so this is like topology of this theory, and at least once I have to write Lagrangian. So it's a very simple theory, okay, which is a little bit like a version of chiral perturbation theory, but in chiral perturbation theory, you take all possible terms in the derivative expansion, okay, in the momentum expansion. And here we have only 4 terms which respect Lorentz invariance and respect the fact that it contains at most first time derivative squared. Okay, so only these terms are here accepted. So it's a very limited number of terms and very limited number of free parameters, only 4. And our hope is that this is enough to describe baryons, light atomic nuclei, heavy atomic nuclei, and even nuclear matter at high density in neutron stars. So it's an extremely constrained model. Okay, there are very little flexibility. So this L is like left current, so it's a derivative, basically derivative of the SU2 field. B is the topological current. Okay? And the solution of this theory with non-zero topological charge are called skyrmions. Okay, and they are classical solitons with this baryon charge. Okay, because you are very interested in knotted solitons, so they are knotted solitons in this model as well, but they are unstable. They are like Sphaleron solutions. They can have finite energy, but if you kick them, they will decay. And yeah, their role in this theory, okay, this is unknown. We don't know what kind of nuclear physics phenomena, for instance, would be behind such knotted objects here. Okay. And this theory is proven to be quite successful. Okay, we can describe baryon physics, so like particles with baryon charge 1. Okay, many of them. Light nuclei, not so light nuclei like carbon-12. I will show a picture later. Many other properties. We can also compute binding energies of atomic nuclei. This is a recent progress, and nuclear forces, and even quite, if you apply this theory to neutron stars, you get very good agreement with available astrophysical data. So it's a powerful, quite powerful, non-trivial theory with only 4 parameters. Right? I would like to underline it, because in the chiral perturbation theory, you easily get 100 terms with 100 free parameters, which are fitted to experimental data. Okay, so here there are only 4.
Can I clarify? So in the original theory's term, added non-linear terms.
Mm-hmm.
So this is different, or it's some different way of writing? Or?
It's almost like Skyrm wrote only those 2 terms. Then he added this term, which gives mass for pions, because pions have mass, non-zero mass. And this term was added also, not by Skyrm, but quite recently after him. Okay? Because it, for instance, physically, it's like omega meson, inclusion of omega mesons. Okay.
So this was already Naya and Sutcliffe work? The third term?
The third term. No, they didn't. They added raw mesons. So this is another family of mesons. Because of course, you can add, as there are many other mesons than pions. Okay, so you can add more and more mesons. So for instance, Naya and Sutcliffe, they added raw mesons, which are like next a little bit heavier mesons, and they shown that you can get much better results even. Okay, so that was the motivation. But then the theory is more complicated, but still they didn't add new coupling constants, because all coupling constants were related to the former one. So no flexibility. Everything was constrained. Okay? So that was also a great result. Okay, so here is, for instance, skyrmion with charge 12, which represents carbon-12 atomic nuclei. And there are 2 classical solutions, okay? One with this geometry, another with this one, and you see like clustering phenomenon. Okay, so this part is charge 4 part, and it's like alpha particle, and it agrees very well with the concept in nuclear physics that light particles like carbon-12, oxygen-16 is a composition of alpha particles. Okay. But you can ask, it's a completely classical field theory, okay? But atomic nuclei are quantum, are objects with quantum numbers, like spin, isospin. So to really identify, skyrmions with atomic nuclei, you have to quantize them. And this is the most difficult part of the scheme theory, because it's extremely difficult to quantize such a non-perturbative solution. Right? It's completely different than the usual quantization, what people do, for instance, in this ab initio nuclear physics, right? Because here it's each skyrmion, in a sense, it's a new curved theory which you have to quantize. Okay? But the simplest quantization is the following. You assume that the classical solution is a like rigid rotor. Okay, it has a fixed geometry, fixed shape, and you start to rotate it both in physical space, and you quantize this motion, and then you get spin, or in the internal space, in these colors, which represent SU2 directions, okay, in the target space, and then you have isospin, right? But this is a rigid rotor assumption, quantization, which assumes that nothing deforms during the rotation, right? And yes?
What is the difference between left-hand side figure and right-hand figure in the two figures, in the big two figures?
Left and right? It's the same baryon charge, but it's different geometry. So one of them is global minimum in this topological charge sector. Another one is local minimum. One is stable completely. Another one is unstable. It's a kind of excited state. It's excited. One is ground state, okay, carbon-12 ground state. Another one, this one is the famous Hoyle state of carbon-12. Okay.
What is color here?
Color represents because target space direction. In target space, this is this SU2 field, and sometimes there is more pi1, sometimes pi2, and this represents which pi wins, more or less. Okay, so it's because it's, you know, it's a three-dimensional sphere, so I cannot write arrows, for instance, because it's yeah. So a better so this rigid rotor quantization, it's quite good, but it's not good enough to really describe atomic nuclei. You have to include not only these zero modes, okay, because if you rotate this solution, the energy doesn't change. This is a zero mode. This is a mode which doesn't change the energy. But there are also non-zero modes which cost some energy to be excited, okay? And these are vibrational mode. And here is one possible vibrational mode, okay, for charge 7 skyrmion, which is lithium-7 atomic nuclei, okay? And this mode, okay, this direction does like that. There is a one parameter, and if you change this parameter, this, you know, it's a kind of symmetric solution. If you change this parameter, this solution is squashed, more or less. But if you change in another direction, this solution deforms into two non-symmetric solutions, okay? Configurations. Only this is a solution. These are some deformation of that, okay? It costs energy to deform this soliton into this for instance, two solitons, or into this squashed configuration. Okay? But as you have a quantum object, you have to also include this non-zero energy excitations. And if you include them, you get a perfect agreement with the excitation states of lithium-7. Okay, and that was big breaking through in Skyrm model, like almost 8 years ago, by Chris Halcrow. Yeah.
So you don't have this kind of color scheme to show the ion orientation.
Yeah, this is the color scheme which shows.
But you know, which color corresponds to which pion and things like that.
I don't have the the explanation here, but the colors correspond to directions in the.
So, for example, which ones are anti-parallel?
Good question. I don't remember which scheme is used in these plots. Yeah. But it's exactly like that. I mean, to have, for instance, attractive channel, you have to anti-parallelize these alpha particles, which constituent the larger skyrmion.
So that would mean the one on the right where it has black and white would be the parallel channel. Right?
I think so. Yes. Yes. I think here, for instance, yeah, you are right. Here, it must be in this anti-parallel channel to attract, because you forced them to separate, you added the energy, okay? So if you, I mean, stop to expanding them, they will really collide, and form again this stable configuration. So you see, the vibration, what I wanted to underline is that vibrational modes are extremely important to apply this solitonic theory to atomic nuclei. Without vibrational modes, you cannot have reasonable contact with observational data, with nuclear physics. Okay? They are extremely important.
Do you distinguish proton and neutron in this model? So you have...
Yes, you can.
You also have...
Charge one, yeah. Yes. You have spin, you have isospin due to this quantization procedure. You have them. In the rigid rotor, it's just rotation in space gives you spin. Rotation in colors in iso space gives you isospin. Okay.
So lithium 7 really means 3 protons and 4 neutrons.
Yes. Okay. So that's the motivation to consider closer vibrational modes. Okay? Okay, so let's go to dynamics of topological solitons, and to better understand the role of vibrational modes, not in the quantum theory as there, but in the more general, in any theory with topological solitons. Okay. So now we go to the simplest theory we can imagine, to domain walls. So effectively, we have one-dimensional, co-dimensional one object. Okay. So we can forget about y and z directions, and we can consider only x and t as a coordinates, which will describe in space-time in which our soliton may live. But I want to underline that this is chosen only for simplicity, okay, to plot things easily. This phenomena exists in 2 dimensions, in 3 dimensions, doesn't matter. Okay? So the simplest model with topological soliton is 5⁴ theory. Okay? So we have real scalar field with kinetic term and with potential, and potential is double vacuum potential. Okay, the simplest one, which allows you for topological solitons. You have a kink which goes from a domain wall, which goes from this vacuum to that vacuum, so from -1 to 1, and you have anti-domain wall which goes from this vacuum to that in the other direction. Okay. The profiles are different, but the energy density is exactly the same. So they are like sort of antiparticles to each other. Okay. So they are like skyrmions, let's say, in 1 dimensions, much simpler. Okay. They have topological charge. Okay. Okay. Good. So let's move. One important feature which these kinks have, okay, is that they are topologically stable. You cannot find a soliton with this topological charge lighter. And to show that, you can take your model, okay, the energy, assuming static solutions, you take the energy and you do a trick. Okay, you write it as a derivative plus this part squared, and you have to, if you make this squared, so you have phi x squared, which is what you had. You will have this bracket squared, which is the potential, and there is a mixing term. You have to subtract it, okay? And then you have exactly the energy you started with. And now this part is bigger or equal to the modulus of the last part, okay? Because this part is integral of a positive function. Integral of a positive function is a positive number. So this expression is larger than that, okay? But this you can compute. It depends only on target space integral, and you can relate it to topological charge. And this inequality becomes equality if this part, this integral is zero. But this integral is zero if and only if the bracket is zero. Okay, so you have this condition. And this is a famous Bogomolny equation, which exists in many other theories in higher dimensions as well. Okay? And it gives you exactly the kink and anti-kink I plotted before. So what does it mean? It means that in a topological charge 1 sector, you cannot have a lower energy solution because this inequality is saturated, okay? There is no lighter solution. So this is completely, ultimately, totally stable soliton. It will never disappear, okay? So, yeah. So we have these kinks, and you see, of course, the theory is Lorentz in Poincare invariant. Okay, you can put soliton at any place in the space, and the energy is unchanged, right? It's constant. This is trivial observation. So you have a whole family of energetically equivalent solutions, parametrized by the position of the soliton. But this is trivial. Okay. Doesn't matter in which place in space you put soliton, the energy is the same because theory is Lorentz invariant. Okay, just for terminology, I will call a theory BPS theory if there is a non-empty set of Bogomolny of solutions which saturate corresponding or pertinent Bogomolny equation. Okay, it's not trivial. Not all models have this kind of property. Okay, so we have soliton in single solitonic sector. This soliton is BPS. Okay, whenever it doesn't matter where you put it, its energy is the same. How this soliton can interact? There is first static force. If you imagine that you have kink here and put another soliton, anti-kink, far away, they will start to attract each other. It's not a static solution. Okay? They will attract. If you have a more complicated theory and you have kink and another kink, they will, for instance, repel. Okay? So there is a static force which, first of all, brings or repels the solitons and also deforms them. Okay, the shapes are deformed. So it's of course, one conclusion is that if you have kink and anti-kink, they are not any longer BPS solution. Okay, because they want to attract each other. There is a attractive force. So here is kink and anti-kink. Okay, as a static configuration, if you plug it into your field equations, they will attract and they will start to move towards each other. Okay, so it's not a static solution, and therefore, if it's not static, it's not at all BPS. Okay, of course, the energy would depend whether kink and anti-kink is far away or close. You see, this is your guessed configuration. It's not a solution, it's guessed configuration. And if a, little a is 0, then tanh x minus 1, tanh cancels and it's -1. It's just a vacuum. And vacuum has energy 0. Okay, so the lowest energy state you can imagine is 0. You cannot, but initially you have kink and anti-kink. If A is very large, you have kink and anti-kink. Each kink separated from another kink has this 4 divided by 3 energy. So the energy depends on the distance between kink and anti-kink. Okay? In this 5 to the 4 theory, generic situation that solitons attract or repel each other, but there are classes of solitonic models where solitons do not interact statically with each other. Okay, there are very famous theories like Abelian-Higgs model of vortices at critical coupling, like Polyakov monopoles, like CP1 sigma model. There are very distinct and famous and mathematically or physically important. And then solitons do not feel forces between each other, static forces. Okay, so we have static force. We have this internal degrees of freedom. What static force does? It makes a soliton to move. So soliton, you can think about soliton as a particle, which starts, you can reduce it to a particle, okay? And this particle feels another particle, they attract each other, they move. But soliton is much more than a point particle. It is a particle with internal structure, okay? Soliton is extended. So it has this internal vibrational modes. And to find them, what we do is we take static configuration, okay, static solution like king, we add a small perturbation, we plug it to the equation of motion and expand everything in the perturbation, assuming that we leave only the linear terms, and then we find something like Schrödinger equation for small perturbations. Okay? And you solve this equation and find all possible modes. You can find zero mode, which is exactly the mode saying that if you kick the soliton, it will move with constant velocity because it's second order dynamics. There is can be unstable mode, for instance. Okay, so that would the meaning of that would be that the soliton is not really stable. There is an unstable direction in which the soliton would decay. There can be some discrete modes. Okay, we call them shape modes. It's like modes in a potential well for the Schrödinger equation. Okay, the discrete modes, and this is the internal modes of soliton. It's a mode. It's like this vibrational modes. If you kick a soliton, it can start to vibrate. Okay, if sometimes a soliton has many such modes, so it means that there are many possible vibrations. It's like spring. Okay. And then above that, there is a continuous spectrum of excitations. It's radiation. Right? It's a very important, there's a very important difference between these shape modes, which are discrete modes, and they are localized on the soliton, okay? And radiation, which are modes which can travel from soliton to infinity. Okay, one of these modes are trapped on the soliton, they can never escape. Another mode, the radiation modes, are modes which go to infinity. They dissipate energy from soliton. Okay, and then we have exactly this radiation. So once soliton interacts, okay, all these three possibilities are coupled together, of course. You have soliton and you want to collide it or put it in the presence of another soliton. Of course, they will attract, for instance. Once they attract, they can collide. Once they collided, what can happen? They had some energy, and this energy can excite some of the internal modes. Okay, so they start to vibrate, but they vibrate. They can also lose some energy via radiation, and this radiation will meet radiation emitted from one soliton can meet another soliton, and now it's really a mess. Okay, so all these three ways of interaction are coupled, making the dynamics of topological solitons really complicated. Okay, so this is like the setup. Okay, so let's see what vibrational mode can do in in the dynamics of topological soliton. We have three ways of interaction, and now we concentrate only on one with this the role of internal degrees of freedom of the vibrational modes. Okay. So again, the simplest situation is soliton anti-soliton collision in 5⁴ model. Okay. So what you do, you have this simple field theory. You have soliton king or brain here, another anti-brain here. Okay, so you have this precisely this situation as your initial setup. You have brain far away from anti-brain initially, but you give them an initial velocity. Okay, you collide soliton with anti-soliton. So this is the time. The color is the value of the field measured at the it's a value of the field, and this is the x. Okay, so at initial time you had a -1, then you go to 1. So this is the king, and there is a 1 1 1 1 1, and then from 1 to -1 there is anti-king. So this line is the position of king. This line is the position of the anti-king. Okay, they have initial velocity constant, as you see, and they approach each other. Okay, and then approach each other, go through vacuum, -1 vacuum. Okay, and then they reappear. They collide and they reappear. It's almost elastic scattering. It's not completely elastic because the velocity, initial velocity, is not like the final velocity. Okay, but at least the particles reappear at the collision. Okay, you see that here are little waves. So this is the radiation emitted in the collision, and also you can see that there are little wobblings here, and this is a vibrational mode excited on the solitons. Okay, so this is exactly what I said before. But if you change the initial velocity, funny things start to happen. So for instance, the king and anti-king collide. Okay, they create vacuum. Then they appear again, but they cannot escape, and they collide once again, second time. And then, surprisingly, they can, escape after second collision. You can find a situation with another velocity that they collide 3 times, and then they escape to infinity. But there are also cases where they will collide forever. Each collision costs energy. The radiation is emitted, so finally this soliton and anti-soliton, they will annihilate to the vacuum, and that's all. Everything will be radiated. So this is a very complicated pattern, completely different than in Sine-Gordon. In Sine-Gordon, if you collide king and anti-king, they will pass through each other with some phase shift as an only effect of the collision, and nothing more. Okay, because this is a integrable theory. This is non-integrable theory, and therefore particle can be created, can be annihilated. But this is life, right? It's really life.
Numerical simulation.
This is numerical simulation, full field theory. Right?
So does it have some kind of analogies on shallow water waves or whatever that would be somehow giving you visual insights into these types of models? I think so. This shallow, there is this famous KdV soliton, which is in this shallow channel. You can create it in shallow channel. Unfortunately, it's an integrable theory. So if you scatter 2 solitons, they will just pass through each other and no effect. So. Well, because you have some parameters you can choose. You can see this and that, and I'm wondering, if those are observables, in some experimental systems that are related to. No, I would say the 5⁴ theory is the simplest model you can imagine in many physical systems. So it's observed. Yeah. It's model. I would say
it's parameter independent. The only parameter which is changed here is just the initial velocity of solitons. Okay, so it's like it.
And then, you know, you in the beginning were saying, oh, you know, we do it in this one dimension, but, you know, it is just like that also in high dimensions. But then you have all kinds of symmetries and directionalities of how they approach. So I think there should be, you know, in a way, big differences.
In a way, there will be big difference, but the mechanism which I will explain, which stands behind this, what happens here, that sometimes you have one collision, sometimes two, sometimes infinitely many. This mechanism is, you can find it. It was found in higher dimensional theories, and you see that it can lead to the same chaotic pattern. It will be. It doesn't necessarily have to be like here, that you have soliton and anti-soliton, and they will annihilate and reappear. Okay, but you can find other observables which would have a kind of chaotic behavior, which can be explained by the same mechanism. I mean, that's the reason I hope it can be also useful for condensed matter. I mean, observing condensed matter physics. Okay, so anyway, if you now collect all possible scatterings for all possible initial velocities, you will see such a picture. Okay, so here it's a horizontal line is the initial velocity of the solitons. Okay, and this direction is just time, and the color is the value of the field at the origin. So if it's blue, means that, and you, for instance, if it's blue, means that king and anti-king are far away from each other. The value is 1. Okay, so, and you have king, anti-king. Here is -1. Here is 1. If you measure value at the origin 1, it means that king is far away from anti-king. If it's -1, it means that you have vacuum, or they annihilate completely. If there is something in the middle, means that things are happening there. So you see, if the velocity is big enough, the solitons, you have 1 at the origin, then it goes to 0 and -1, and then again to 1. So this is the one bounce scattering. Solitons meet, okay, and then bounce to infinities. But then if the initial velocity of the solitons is small enough, then you can see 2 bounce windows. So they scatter twice. There is 3 bounce windows. There are even 4 and 5 bounce windows. Okay, but between these windows, there are like regions where solitons never have enough energy, kinetic energy, to escape back to infinities. So they will annihilate to radiation. Okay, they will completely annihilate and never reappear as final states. Okay? So in this picture, here is the velocity of kings if they appear as finite states. Okay, if they're 0, means they annihilate. And funny thing is that this is really fractal. There is a fractal structure in this. If you take this, this is the again the velocity or measured velocity of king and anti-king after collision, if they reappear after collision, and numbers or colors just show how many collisions they do. Okay, 1, 2, 3, and so on. So finally, you have only 1 collision. If you zoom this region, for instance, you get this plot. So it's a kind of self-similar structure. Okay, this is this plot is very similar to this one. If you now zoom this, you will see again. So this is a really chaotic fractal behavior hidden in this collision. And how how to explain it. And it can be easily or not so easily explained by the resonant energy transfer between kinetic degrees of freedom of king and anti-king, okay, as they move, and internal degrees of freedom, which is this vibrational mode. Okay, you can excite. So this is a bit like your reduction of motion of planar skyrmion, but this is not only the position, but also internal degrees of freedom. There is something more which we have to add to explain this chaotic pattern observed. Okay, so we have kinetic degrees of freedom, zero mode, which is position of the solitons, and we have amplitude of this mode, internal mode, which is hosted by the soliton. Okay, so you can reduce your field theory to two-dimensional like mechanic system, okay, point particle like system, where you have king, anti-king at given positions, okay, and then you have this internal modes. They have this form, it doesn't matter, but they have this form, and they have like amplitude. So you have two coordinates, okay, one is the position, another one is this amplitude. And now what you do, you take this configuration, plug into your Lagrangian original theory, you integrate over the spatial coordinates, and you assume that all dynamics is hidden in the dynamics of these two parameters, okay, of these 2 degrees of freedom. Okay, so it's a reduction of the original field theory to two-dimensional point particle-like model. And it's not too difficult model, but very, it's also not trivial because, for instance, this function Gij, it's a metric on space where this coordinate lives. Xi is x1 is little I, x2 is big I. Okay, it's just a coordinates. And then you do analysis of this model. Okay, and what you find is this plot. Okay, so now you have a model with only 2 degrees of freedom. You assume initial conditions for these 2 degrees of freedom. They have to be connected to the initial conditions for the full field theory, right? And you compare what you find. And this is the plot you can derive in this simplified theory. So qualitatively, it's really the same. It's you see one bounce scattering, okay, and if the initial velocity is smaller than a kind of critical value, then you see 2, 3, and higher bounce windows. You see these annihilation regions, and yeah, that was the result. Like kind of, it's not a mathematical proof, but it's a good evidence that the fractal structure, the chaotic structure observed in the king-anti-king collision is really due to the resonant energy transfer between kinetic and internal degrees of freedom. Okay, it's a good evidence.
Sorry, do you have the same chaos characters between those 2 figures? I mean, for example, dimension of the chaos structure.
Dimension of
the scale dependence or something. I don't know how to characterize the
chaos. No, we didn't study this. For instance, one thing you can do is you can compute this Hausdorff dimension or something more refined. Yeah, and some people do it for soliton collisions. Yes, but for this simplified model, okay, for the explanation of the fractal structure in the 5-to-4 theory, we didn't do this. We were too happy with this result. It was like 40 years problem in mathematical physics or solitonic physics that yeah, no one was able to reproduce this full theory result in a kind of reduced dynamics. Okay, so
how can we understand why the chaotic property appear in this dynamics when I look at the reduced theory?
The chaotic is the following. I mean, if the situation is like follows: if you scatter solitons, they meet, and now they some part of energy, kinetic energy, goes into the vibrational mode. They bounce, and if too big fraction goes to the vibrational mode, they cannot escape. They have too little energy, too little kinetic energy, okay? Because remember, it's a king and anti-king, they attract each other also. So they have too small kinetic energy, they cannot escape. So they collide once again. And it can happen that during this second collision, energy stored in the internal mode goes back to the kinetic mode. And then they have kinetic energy large enough to escape, and they escape. But it depends strongly on the time which is between the first and second collision. Okay, so that's a very fragile system, and you have to be really, you know, in the good phase to transfer the energy from internal to the kinetic degrees of freedom. That's how the mechanism looks like. But why it's exactly fractal structure there, it's an open question. Yeah, it's unknown. Like from the real mathematical point of view, we don't know why, because you can expect chaotic without this self-similarity. But yeah, this is not explained, yeah. So one, like, of course, one consequence that this reduction works is that this model is quite simply, it has only 2 degrees of freedom, not infinitely many like field theory. So it's much simpler for mathematical analysis. So yeah, this is like obvious continuation or application of this reduced model. And it was really like surprised that such a violent process like annihilation in a completely non-integrable theory can be described by only 2 degrees of freedom. Okay, it's really like unusual. Yeah, basically when we started this project, we thought that it's impossible. It cannot happen that collective coordinate approximation, that you take only 2 collective coordinates, for instance, cannot handle such a complicated behavior. But yeah, it works. So, and now comment about higher dimensions. And yes, this kind of resonant energy transfer was observed for higher dimensional solitons. And there is a paper by Paul Sutcliffe from this year. It was like March or May, I don't remember. And he has planar solitons with internal U1 rotation, and then he observed exactly this kind of resonant energy transfer, not in the soliton anti-soliton collision, but in a soliton-soliton collision. Okay, and there are some observables which can which may have a kind of this kind of chaotic or fractal behavior. Okay. So how much time do I have? 5 minutes. So okay, I will finish in 5 minutes. So you can wonder what. Okay, you can ask one question. Okay? If you think a little bit, you started with this configuration. King has its vibrational mode. Okay, if you perturb it, it has this vibrational mode. The anti-king has also vibrational mode, but when they meet, they form for a very short time, they form sort of vacuum. Okay, the configuration is almost like -1. There are some wiggle, yeah, wobbling perturbations, but yeah, let's say it's a vacuum. But vacuum doesn't host any mode. It's just a vacuum. It's a constant value of field, no modes. So you could say come on, it cannot work at all, because you started with a situation where the modes exist, okay? And now you pass through a configuration where there are no modes at all, okay? So why this work at all? And whether there is a like theory where the fact that the mode disappear makes any sense, and it's important, because you see, your mode has to disappear between this situation and that situation. Dynamically, at some point, this mode disappears. So in this collision, okay, in 5⁴ collision, it doesn't matter, because the collision is very fast, okay? When king meets anti-king, they attract strongly, and if you naively consider what is the, it's a naively, you cannot do this, you shouldn't do this. If you compute the speed of the center of the soliton, okay, here, so the position of 0 of the field, it will be like, almost like speed of light. Okay, it's extremely fast, very fast collision. Although you started with, for instance, non-relativistic velocity, but in the moment of collision, situation is really, everything happens very quickly. Okay, so the system basically doesn't know that the modes disappeared. Okay, but if your collision would be very slow collision, even at the moment where the soliton and anti-soliton collide, right, annihilate, even at this moment, then the system has a time to realize that the modes disappeared, and then this fact of disappearance of mode can be important and can influence the dynamics. And I skip everything, okay, and I show only situation where there's a modification of this 5⁴ model in such a way that we added impurity into the system, so like a fixed distribution of matter, such that this shape mode hosted by king enters the continuum spectrum. Okay, so maybe at some distance from this impurity, the mode enters the continuum. It becomes, let's say, like radiating mode. Okay, it's not completely true, but it's something like that. Okay, but anyway, at this distance from the king and impurity, the mode doesn't exist. But the velocity is so small that the king knows that it lost its mode. Okay? So it can be reflected at this point. And this point can be really far away from the impurity, which is located at the origin. So there can be really far away, long interaction between king and, in this case, impurity, okay, due to the transition of the mode to the continuum spectrum, due to the disappearance of normal mode, of the shape mode. Okay, and this is I explained. This is the position of the soliton, only position. So if you excite the mode sufficiently, this king will be reflected at the point which is really the point where the mode is not a mode any longer. It goes to the continuum spectrum. Okay, and this is for like modified 5⁴ theory, okay, with this impurity. But then we found this phenomenon in many theories in one dimension, and you can find it, it is the most exciting, in the Abelian-Higgs model at critical coupling, okay, for vortices. And it's due to the fact that vortex of charge 1 has one mode, one internal mode. Vortex of charge 2 has 2 internal modes, and vortex of charge 3 has 2 internal modes. And now imagine that you scatter vortex of charge 1 with vortex of charge 2. in the abelian Higgs model at the critical coupling, which means that they don't attract statically each other. So it means that the process of collision can be very slow. Okay, they will never accelerate due to the static force. Okay, so they collide, they will form a topological vortex with charge 3, but this vortex has only 2 modes. This vortex has 1, this has 2. So initially you had 3 modes. At some point you have only 2 modes. So one of these modes must go to the continuum spectrum, must disappear. So you will see this effect, the spectral wall, exactly in the abelian Higgs collision of the abelian Higgs vortices. And there is a group in Edinburgh which is doing that, and hopefully there will be paper in this month. They promised it like 2 months ago and still they didn't put, but yeah, I expecting so. Thank you very much.
Okay, thank you.